The European Space Agency's automated transfer vehicle has a crucial role in maintaining human spaceflight operations on the International Space Station, humanity's permanent outpost in space. Each ATV is named after a scientist or individual who fundamentally changed the way in which we understand the universe. And this series of films aims to examine these scientific breakthroughs and visionary concepts that made history. If we journey back in time 4 centuries, Europe was undergoing an era of profound change and intellectual revolution. Just as the Renaissance was transforming the world of literature and the arts, so Johannes Kepler would transform the world of observational science. Born in 1571 in the German town of Weil der Stadt near Stuttgart, the 6-year-old Kepler saw the Great Comet of 1577, an event that was to shape the direction of his life's work and, as a result, the way in which humanity sees its own place in the universe. Inspired by this celestial spectacle, Kepler fell in love with physics and mathematics, convinced that by careful analysis of the stars and planets in the night sky, he could deduce the mathematical basis of the universe. For thousands of years, sky watchers had noticed that, although most of the stars seemed fixed in position, 5, Mercury, Venus, Mars, Jupiter, and Saturn, were most definitely not. Traversing across the star fields in broad, curving paths, occasionally reversing in direction, these planetes, the Greek for wanderers, would provide the key to Kepler's discoveries and also the more familiar term, planets. By the 16th century, 2 conflicting explanations had emerged to try to decipher the celestial dances of the planets. The orthodox Ptolemaic model put the Earth at the centre of the universe, whilst the revolutionary Copernican model had dethroned the Earth and humanity from this central position, replacing it with the Sun. Arguments raged, but critically, both models relied on the idea of purely circular orbits. And they both seemed to work as alternative explanations of what was being seen. Almost, but not quite. Both the models used circular suborbits called epicycles to try to explain the observed motions of the planets in a desperate attempt to fit the circular model they believed in. But as observations became ever more detailed and precise, so the deviations grew. It was Johannes Kepler who broke the paradigm in 1605 and explored a new way of attempting to understand not only the motion of the planets, but also the trajectories of every object in the universe. But how? Nowhere was this problem more obvious than in trying to explain the observed motion of Mars. Kepler spent 6 years and thousands of pages of calculations, and his solution to the mystery of the red planet's orbit manifests itself in his 3 laws of planetary motion. Firstly, the orbit of Mars isn't a circle, it's an ellipse with the Sun at one of its foci. Secondly, a line joining Mars to the Sun will sweep out equal areas in equal times. Furthermore, Kepler later realised that this didn't just apply to Mars, it applies to all the objects orbiting the Sun. So for a comet with a highly elliptical orbit, Kepler's second law means that as it approaches the Sun, It races inwards with an increasing velocity that then dramatically reduces as it returns to the cold depths of the outer solar system. Kepler's subsequent analysis of all the known planets led to the third of his laws. The square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. But what does that mean? Well, a planet closer to the Sun will not only orbit faster than an outer one, but its angular velocity will be greater. It'll race ahead along its orbital racetrack path. A discovery that successfully explained the Martian orbital mystery without any recourse necessary to the convoluted theory of epicycles. By the painstaking analysis of observational astronomical data, Kepler had unlocked the secrets of planetary motion decades before Sir Isaac Newton provided the ultimate proof of why through his universal law of gravitation. Many centuries later, it's the mastery of applying Kepler's three laws that enables the European Space Agency to launch its ATV, or Automated Transfer Vehicle, to rendezvous with the International Space Station. The 5 ATVs are named after European scientists and visionaries of space exploration, including Kepler. And each of these vehicles is launched from Europe's spaceport in Kourou in French Guiana, aboard Ariane 5 rockets. After launch, each ATV spends more than a week catching up with the ISS in an outward spiral path over 4 million kilometres long, with velocity reducing as altitude increases, obeying Kepler's third law. Using its GPS and star trackers, ATV's onboard systems are aiming to intersect the orbit of the giant space station at an altitude of nearly 400 kilometres and a velocity of nearly 8 kilometres per second. And during this time, the ISS completes more than 100 orbits of the Earth. ATV makes its final approach to the station, its onboard computers using a range of navigation systems to ensure a closure rate of less than 10 centimetres every second. With contact and capture complete, the 20-ton vehicle has fulfilled one of its primary objectives: the delivery of essential cargo and experimental supplies for the inhabitants of humanity's farthest outpost. But its orbital duties aren't over just yet. We often think of space as being a vacuum, but even at an altitude of 400 kilometres, there's a minuscule amount of atmosphere present, enough to cause a measurable drag force on the ISS. So what effect does this have? Well, from Kepler's and Newton's modelling, a reduction in orbital velocity causes a drop in orbital altitude. And in the time that I've been talking to you, that figure for the ISS is around 20 centimetres. Now that doesn't sound like much, but let's keep adding up the numbers. Over a day, the height drop is that of a 20-storey building. Over a week, nearly half a kilometre. To counteract this orbital decay, ATV has a key role in preventing this through orbital reboost. By firing its engines in a series of extended burns, ATV accelerates the entire 420-ton mass of the station by an extra 70 kilometres per hour. After the reboost, ISS stabilises into an orbit approximately 40 kilometres higher. And, following Kepler's third law, its new orbital velocity is actually less than before the reboost. There's one final role for each ATV, and once again, it relies on the precision and application of Kepler's laws. During the many months that each ATV is docked with the ISS, its shirt-sleeve pressurised environment, having been emptied of cargo, is progressively filled with waste material. ATV's final act is to unberth from the station and reduce its orbital velocity. The resulting drop in orbital altitude subjects it to ever-increasing atmospheric drag. Ram air compression, often referred to as atmospheric friction, caused by its hypersonic velocity in the upper atmosphere, results in enormous aerodynamic, mechanical and thermal stresses. So much so that ATV's decaying orbit will eventually destroy the vehicle. The re-entry is targeted over remote areas of ocean to minimise any risk of debris damage. Its mission complete, ATV's final breakup is a spectacular display, visible from both the surface of the Earth and the ISS itself. ATV's tasks are finally completed, thanks to the combination of Kepler's laws and European engineering excellence.